Hi everyone, and welcome to the second of two videos going through exam questions on enthalpies of solution and enthalpies of hydration. So the first bit we've got here is making sure that we actually know the definitions for these enthalpy changes. Okay, so it's similar to, we've seen the definition for lattice enthalpy come up over and over again. Definitions of these two don't come up as often, but you do still need to know them. They could come up. And it's easy marks if you do learn them. So the enthalpy change of solution is the enthalpy change that occurs when 1 mole of a compound is completely dissolved in water. So it's basically, forming a solution. So it's the enthalpy change when you take a solid and turn it into a solution. Okay, but specifically 1 mole. The enthalpy change of hydration is the enthalpy change that occurs when 1 mole of gaseous ions forms 1 mole of aqueous ions. Okay, so it's just ions in the gas state turning into ions dissolved in solution. Okay. So it's worth learning those definitions. They're easy marks if you can remember them. And then this is a similar question to the one we saw in the previous video. We're comparing the enthalpy of hydration values for two different ions. And so it's the same factors that it always is. It's charge and its radius. Okay. So obviously let's start with the charge. That's clearly different. So Mg2 plus ions have a higher charge than Na plus ions. And then the other thing is the radius. We've seen sodium and magnesium compared before in previous videos. They're in the same period. Remember, as you go across a period, the radius decreases slightly. So the magnesium ion is also slightly smaller than the sodium ion. So magnesium ions have a higher charge than sodium ions and a smaller ionic radius. So magnesium ions have a stronger attraction, and this is enthalpy of hydration, remember, so it's a stronger attraction for water molecules meaning the enthalpy of hydration for magnesium is more exothermic than for sodium. Okay. And so it's important that we link these things together. Okay, that we talk about the radius and the charge. Those are the two important factors. We link that to attraction specifically for water molecules because it's hydration. And then we also need to say, okay, if there is a stronger attraction, what is that going to mean for the actual values? A stronger attraction means it's going to be more exothermic, okay, because more energy is going to be released when that attraction is formed. Okay, moving on with this question. The next thing we have is another one of these fill in the gaps on the diagram questions. So what's going on here? This is the lattice enthalpy. So it must be formation of 1 mole of a lattice from its gaseous ions. So here we must have magnesium as gaseous ions, and this is 2 hydroxide ions. And this is the other reason why it's really important that you learn the definitions, because obviously it helps you with the definition question, but if you know that lattice enthalpy is formation of 1 mole of a lattice from its gaseous ions, then you know what you need to write here. And then these two processes will be enthalpy of hydration of each ion in turn. That's why they end up both aqueous at the bottom here. And it doesn't matter which order we do them in. So I'm going to do magnesium first, make that aqueous, but leave the hydroxide as a gas. and then this process represents the hydration of the hydroxide ions. Okay, and now we need to calculate lattice enthalpy. So this is the last one of these calculations that we need to do. Let's just get the numbers on here. So what have we got? We know the enthalpy of hydration of sodium, that's not actually relevant in this case. The enthalpy of hydration of magnesium is minus 1926. So that is this process here. The hydration of the hydroxide ion is minus 460. So that's this one. But that needs to be times by 2 because there's 2 hydroxide ions. And then we need the lattice enthalpy. So we're looking for this value. We're looking for the enthalpy of solution of magnesium hydroxide. Where does it say that? Doesn't say it here anywhere. Does it say it? Must be back on this page somewhere. Oh yeah, here we go. So it's minus 152. Okay, so just look for these. They kind of hide it. I don't know why they haven't put it in the table there. I guess these are all enthalpies of hydration, so that's why. But yeah, just make sure you can find the missing values here. So this is minus 152. Right, so then let's just copy these numbers and decide what we're going to do with them. Well, we always just write these numbers down and then we make a decision whether we want to be adding them or taking them away. What are we actually trying to calculate? We're trying to calculate lattice enthalpy, which is this one. So we're starting here and we're ending here. And this is the one we want, so we're going to have to go the opposite way around. So we're going to have to go down here and then down there and then back up that one. So these two arrows are in the same direction, so we can add that one on. These two arrows are in the same direction, so the minus 460 can be added. And then the minus 152, we're going the wrong way. So that one's going to have to be minus 152. Okay, let's calculate that. So we've got minus 1926 plus 152 minus 460 times 2. We get minus 2694. That is a lattice enthalpy value. We know that lattice enthalpies should be very negative. There's a massive white space here for some reason. We know it should be very negative. So that looks like a sensible answer.